In this lecture, we will learn how to compute the sample size when our goal is something related to a variance. So we will study several cases. So one sample, two samples with variance, and then we will see the coefficient of variation. So let's start with one sample. So let us assume that we are manufacturing syrup whose concentration, the mean concentration, should be 3 milligrams per milliliter. So we know that the standard deviation of the manufacturing process should be around 0.1 milligrams per milliliter, and the deviations from the target should follow a Gaussian distribution. We wonder how many samples do we need to screen if we want to detect an increase from the target standard deviation of 50%, and we want to have a power of 80% and a confidence level of 95% if this increase happens. So this increase of the standard deviation means that the standard deviation goes from 0.1 to 0.15. Okay, so let's see how to do these calculations. So we need this test is of this form, and then we need, as always, to know how a given statistic is distributed when the null hypothesis is true. So when the null hypothesis is true, this calculation, that this is the sample standard deviation divided by the target standard deviation, should follow a chi-squared distribution with n minus 1 degrees of freedom. So this is this distribution here. So here we have the what would be the distribution of this calculation when the null hypothesis is true. When the alternative is true, then it would be distributed like this. This has been chosen as a function. Here what we see is s squared, and what we have chosen here is a larger standard deviation, so 0.15 standard deviation. The s squared is 0.15 squared, and then we need to find a critical value such that from that critical value to the right, when the null hypothesis is true, the area is alpha, and from that critical point to the left, when the alternative hypothesis is true, that area is beta. And then we should find this critical value, and this critical value will give us an equation from which we can solve for n. So when n increases, the shape of these two curves change, and then we will be able to find this critical value and the n such that from that point to the left is beta, from that point to the right is alpha. And yeah, it is not an easy task, but what we have to find is n such that this equation is satisfied, and sigma 1 is the one at which you already want to have this statistical power. So we see that sigma 1 somehow is related to this statistical power there. And when n is large, then we can approximate the n that solves this equation in this way. And we see that this already follows the strategy that we had for sample means. So when we were trying to calculate the sample size for the comparison of two means, so the structure there was a term related to the confidence level and in a Gaussian way, so that is why we use Z. Then a term related to the statistical power divided by the effect size, and this effect size in this particular case it is like this, but it is very interesting because it follows the same kind of philosophy that we had for means. And then, for instance, here the exact solution gives n equal 19, and the approximate one is also n equal 19. So we have now a very useful tool because we can validate our sample size calculation done with a program through some easy calculation that we can do by hand. And when we have a one-sided, here there is a mistake in the equation, but when we have a one-sided tail test, we have this equation here, this equation there. They are almost the same, but you see that there are small differences, like 1 minus alpha, this is beta, this is 1 minus beta. So it depends on which side you are looking at. So and then when you have a two-sided, what you have is a mixture. So you calculate n for this one, n for this one, and then you take the maximum of the two. And what happens if we have two samples? So if we have two samples, for instance, let's say that we are considering buying a new analytical machine. We wonder if the new machine reduces the variance of the measurements by at least 50%. How many samples should we evaluate with each one of the machines, and we are given some statistical confidence level and power. So the difference with the previous case, in the previous case we were comparing one sample to a reference value. Here we are comparing two samples, so we will compute the variance in one of the groups, the variance in the other group, and we will check whether the variance in one of the groups is larger than the variance in the other. And if it is larger by more than 50%, then we want to have this statistical power and this confidence level. So instead of the chi-squared, now the appropriate statistic is Snedekor's f, and so we will have this S1, that is the sample variance in group 1 divided by sigma 1, S2 divided by sigma 2, and this ratio will have n1 minus 1 and n2 minus 1 degrees of freedom. So, but the idea is the same. So we can express that that equation there, that test in a graphical way. So if the null hypothesis is true, so if the two are if one of them is smaller than the other, then this ratio, this is s1 squared divided by s2 squared, should be smaller or equal 1. While if it is larger, this is that, if this is larger, sigma 1 is larger than sigma 2, we should see that this ratio moves to the right, and then we have to find this critical value such that from that point to the left is beta, from that point to the right is alpha, and we are used to this kind of calculations. We have to find n1 and n2 that satisfies this equation. If we make both groups to have the same size, then we have an equation that the only unknown is n, and we have the ratio between sigma 1 and sigma 2 that we already know, because we are given this ratio here, so one should be half of the other. And yeah, and again there is an approximate method that approximates this n for large n with something that is related to the sample size of a mean. So the term related to the confidence level, to the statistical power, and then some normalization of the effect size. So with the exact method we get n equals 74, with approximate we get n equals 72. So we need to take 74 samples from each one of the machines and to detect whether there is a reduction of the variance by a factor 0.5. Okay, so very easy. Last we will see the coefficient of variation. So the coefficient of variation is somehow a way to relate the standard deviation to the nominal value of our measurements. So let's say that we have a value that is centered around mean, so the mean is 1000, and the standard deviation here is 100, the standard deviation here is 10. So these measurements are much more precise than these ones, and a way to express that is to take the standard deviation divided by the mean. So somehow this coefficient of variation is only 1%, so this is standard deviation of 10. When we look at values that go from let's say 9080 to 1020, they're much closer to the mean than these ones, and we can encode that by the standard deviation divided by the mean. So the smaller that value, that is called the coefficient of variation, the more precise our measurements are. Okay, so there is some legislation that allows for analytical errors of 15%. So this is how many samples do we need to take to check if our measurements are compliant with this coefficient of variation of 15%. So we want to have a statistical power of 90% if the coefficient of variation goes up beyond 20%. Okay, so our test is that the alternative is that the coefficient of variation is larger than 0.15, and the null hypothesis is the opposite. Okay, so we can again we need to find a couple of distributions, one for the null hypothesis, one for the alternative, and in this case we will approximate the coefficient of variation with a Gaussian, which is true if n is large, and then the mean of this standard deviation, the mean of this Gaussian should be sigma divided by mu, and the standard deviation will be this one. So yeah, so it is the standard coefficient of variation that we expect times this calculation where n is involved, and then we simply have to use the standard tools for Gaussian designs, and then we need to find this critical value such that from this point to the right we have alpha, from this point to the left we have beta, and we already discussed in the lecture of the means how this point is reached from H0, how it is reached from H1, and then this will give us an equation from where we can solve for n. And this is the solution, and it is much more complicated than we had before, but we see kind of the same structure. So we have the term in the confidence level, we have the term depending on the statistical power divided by some normalized effect size. The problem is that the normalization somehow has gone up, and it is affecting the confidence levels and the term of the statistical power. But okay, it is something a little bit different from what we were seeing for the means, but not so different. Okay, so now we have only to substitute our values. So we the null hypothesis was 0.15. We wanted to have a power of 90% if the coefficient of variation went up beyond 20%, and it is simply just substituting there. We get 54 samples. So this would be all. The exact formulas are not trivial because they involve chi-square distributions, Snedeker's F distributions, but the concepts are the same. You have to find a critical value. The shape of these distributions depend on n, and you have to find a critical value and an n such that from that point, from that critical value to the right you have alpha, to the left you have beta, and there are normal approximations that they all follow the same kind of philosophy. So confidence level plus statistical power divided by the normalized effect size, and they are very useful to validate the results that you compute with the computer. And there is a problem, that is that if the two sigmas are very close to each other, then the number of samples grows very quickly, and this is understandable if the two sigmas are very similar to each other. So we are trying to detect very small differences in the standard deviation, and small effect sizes should rapidly translate into a growing n. So this would be all for the variance, and see you in the next lecture.